Hello, it's Stat 134, Lecture 9. So last time we did some harder hypergeometric and counting problems from section 2.5. We're going to finish section 2.5 today, talking about the binomial approximation to hypergeometric. And then we're diving into chapter 3, which is about random variables and joint distribution of two random variables and independence. So binomial approximation to hypergeometric. So remember that the binomial distribution has independent trials, whereas the hypergeometric has dependent trials. So we're drawing with replacement or we're drawing without replacement. So suppose you have a 100-person class with a grade distribution with 100 A's and 30 with 70 A's and 30 B's, and we sample 5 students at random without replacement. We want to find the probability that we get 3 A's and 2 B's. So this would be done exactly using a hypergeometric. So you'd have 70 choose 3 times 30 choose 2 over 100 choose 5 by the hypergeometric formula, which you can also write as 5 choose 3, 70 over 100, 69 over 99, and so on to 29 over 96. But you could approximate this with a binomial, and you would see you get something very similar. If we imagine that we're drawing with replacement, then the 69 over 99 would be 70 over 100, and the 68 over 98 would be a 70 over 100, and the 30 over 97 would be 30 over 100, and so on. So you would just get the binomial formula. So when n is large relative to small n, the hypergeometric is quite close to the binomial. And to be specific, hypergeometric 175 is approximately binomial 5.7. So the reason is because without replacement becomes very close to with replacement when the population size is large and your sample size is small, because when you have without replacement and your population is big and your sample size is small, it's very unlikely you're going to, let's just say if you're drawing with replacement, it's very unlikely that you would draw the same ticket twice, right? So with replacement is very close to without replacement, and so hypergeometric n g little n is close to or approximately little n g over n. So summary of approximations that we've seen, we have hypergeometric, big N, big G, little n, is approximately binomial when n is large and small n is small. And probability is capital G over n, so we get binomial NP then. If p goes to 0, n goes to infinity, and then p goes to mu, we get a Poisson, and we get normal if mu plus or minus 3 sigma is between 0 and n, and here we're letting mu be np and sigma be square root of npq. So now on to chapter 3.1. So here we're talking about a random variable, x, which is, you can think of it as the outcome of an experiment. For example, you flip a probability p coin 2 times, x is the number of heads. So x equals 1 is an event, and the probability that x is 1, you could find using the binomial formula, and we write x is binomial 2p, because so the squiggle means belongs to, and that is because the probability distribution is following from the binomial formula, with n is 2 and p is whatever the probability that you flip ahead. But to be more precise, a random variable is a function from your outcome space to the real numbers, and x is counting the number of heads, so that defines this function. So x equals 1 actually means the preimage of x, the preimage of 1 under x. So what maps to 1? Well, ht and th map to 1. So that's what the event x equals 1 is. And we can write out the distribution. So x is probability distribution. It takes values 0, 1, 2, and it has probabilities 1/4, 1/2, 1/4, 1/2 because we're looking for the probability that we have ht or th. And just to mix things up, we can define a function of x, which will be another random variable. You could call it y if you want, or g of x. Let's say that's the absolute value of x minus 1. So x here is still the number of heads, and the absolute value of x minus 1, well, I'm not going to interpret some practical application of this, but I just wanted to show that you could define some function of a random variable. So here you can see that it takes values 0 and 1, and you can find its distribution. So its distribution is 1/2, 1/2, because the probability of having a 0 is 1/2, and the probability of having a 1 is 1/4 and another 1/4. So what's the distribution of absolute value of x minus 1? So you can see from the 1/2, 1/2, and the taking its value 0, 1, that this is just a binomial 1, 1/2. So now for joint distributions, let x and y be the joint outcome of two random variables. So when we write x equals x, y equals y, that's the intersection of these two events. So for example, if x is you draw from this box one with 1, 2, 2, 3 in it, and given x is x, y is the number of heads in x coin tosses. Okay, so now so there's a natural ordering from this that we can find y if we know x. So the probability that x is x and y is given by the multiplication rule, where the probability of y is y given x is x times the probability of x is x. So for example, the probability that x is 1, y is 1 would be to say is the probability that I have a single coin toss that's a heads times the probability of choosing a 1 from this box. So I get 1/2 times 1/4 is 1/8. So then I had you guys fill out some of these. So these are pretty straightforward. Let's do, for example, probability of getting x is 2 and y is 1. So probability 2, 1. So probability of getting a so 2, 1 means that so 2, 1 means that I've chosen a 2 from the box and I get, so I am rolling the die twice and I get a 1 heads. So the probability of rolling the die twice and having 1 heads is 1/2, and the probability of getting a 1 from this box is also 1/2, so I get 1/4. Okay, and you can check all the other ones, and we can fill out this joint distribution table. So the center of this table are all of these joint probabilities. So if they're impossible, such as x is 1, y is 2, right? It's not possible that I have 1 roll and I have 2 heads. So I will put zeros there. Notice that all the entries add up to 1. And in the margins above and to the right, I have marginal probabilities of x and y, which is defined as, so the marginal probability of x is you fix your x and you add up all of the entries in the column above. So we can do this, and for y, similarly, we fix y and we add up all of the entries in the row with that y value. So notice that x minus 1 is binomial 2 1/2 because x minus 1 takes values 0, 1, 2, and it has the distribution quarter, a half, a quarter. To see that it has distribution a quarter, 1/2, a quarter, to see that binomial has that distribution, you can just use the binomial formula as I've written here. Y, the distribution of y is not some named distribution. It looks complicated, so that's okay. So it's just not a named distribution. Are x and y dependent? Well, intuitively they must be, right? Because y is clearly dependent on x. The number of heads that you get depends on how many times you toss the coin. But you can see also that the conditional probability is equal to the unconditional probability. The probability that y is 0 given x is 1. That is a half, since the chance of getting a tails when you flip once is a half. And the probability y is equal to 0, that's a marginal probability that we can see is 9/32. So we have dependence here. So the definition of two random variables are independent if basically the unconditional probability is equal to the conditional probability, or vice versa, for all x and y. So, but a more popular way to write this, by the multiplication rule, if x and y are independent, you can write the joint probability factors into the marginal probabilities. And you can check from the table that that this is dependent because, for example, the marginal probability of a quarter times the marginal probability of 1/32 does not equal 0. So then we did a concept test. The joint distribution of x and y is drawn below. So I asked you if x and y are independent, and you can see that they are by just multiplying you can see that the joint factors into the marginal probabilities. So for example, a quarter is 3/8 times 2/3. A third is 1/2 times 2/3, and so on. You'd have to check all of them. And furthermore, if you have independence, then it shouldn't matter whether you're conditioning x on y is 0 or y is 1. So these must be the same. So actually B follows from A, but you can also check. As I've done here, that they're both 3/8. And I should mention that this is not. You might mistake this to say that the probability that of having x0 is equal to the probability of having x1. You could see that that's not the case here, because the lower row is half of the top row. So, but that's not what it was asking. Second question, a fair coin is tossed twice. Let x be the number of heads on the first toss, y the number of heads on the first two tosses. Okay, so the table is correct. You can check that. So you can figure out what each of these cells are. So for example, the bottom left is tail, because we have x is 0, which means that I have a tail, and y is 0, so that means I have two tails. And so some of them are impossible, in which case the probability would be 0. So yes, this is correct, and you can see y is binomial 2 1/2. Again, we've done this a few times now. So more than one of the above. Okay, guys, great. Have